Hi, this video is to work through an example using joint, marginal, and conditional distributions for bivariate distributions of the discrete type random variables. So mostly what I'm going to do is just work through one long example that has many parts, just to make sure we're clear on when it's appropriate to use a marginal distribution, when we would use a joint distribution, and when we would use conditional distribution to answer a question about probability. So first of all, I'm going to work with this joint probability mass function, f of xy, for the random variables x and y. It's tabulated below. And the first thing I need to do is I need to figure out the value of c in this table. Now, remember that a joint probability mass function, just like any other probability mass function, has to have all the probabilities summed to 1. So to answer part A, what I really need to do is I need to figure out the value of c that will make the probabilities in this table all sum to 1. So if I look at these, I've got 1/20th plus 2/20th plus 1/20th plus 0 plus 0 plus 0 plus c plus 2/20ths plus 1/20th plus 0 plus 1/20th plus 2/20ths plus 3/20ths plus 0 plus 0 plus 0 plus 1/20th plus 1/20th plus 1/20th plus 1/20th. And this all needs to sum, as I said, to 1 in order for this to be a joint probability mass function. So I find that I have 17/20ths plus c must sum to 1, which means that c is equal to 1 minus 17/20ths. So c is equal to 3/20ths. So now I have a fully specified probability mass function for x and y. The next thing I'm going to do is I'm going to find the marginal distribution of x. Remember, to find the marginal distribution of x, what I'm going to do is I'm going to add up all the values over all the different values of y associated with that value of x. So if I use my x, and here's my marginal distribution, f sub x of little x, I can find this marginal distribution. The probability that x is equal to -1 is 1/20th plus 2/20ths plus 1 more 20th gives me 4/20ths, or 1/5. For x equals 0, I've got 0 plus 3/20ths plus 2/20ths plus 1/20th gives me a total of 6/20ths, or 3/10. For x equals 1, I sum all the different probabilities associated with the different values of y. I get 1 plus 2 plus 3, again gives me 6/20ths, or 3/10. And for x equal 2, I get 0 plus 1/20th plus 1/20th plus 1/20th plus 1/20th, that gives me 4/20ths, or 1/5. So here's my marginal distribution of x. Similarly, I can find my marginal distribution of y, f sub y of y, for each of the values of y. For y equals 1, I add up the probabilities associated with all the different x values. I've got 1/20th plus 1/20th is 2/20ths, it's 1/10. For y equals 2, I've got 2/20ths plus 3/20ths plus 2/20ths plus 1/20th gives me a total of 8/20ths. Let me just double check that. 2, 5, yep, 8/20ths, which is 2/5. For y equals 3, I have 1/20th plus 2/20ths plus 3/20ths plus 1/20th. Gives me 7/20ths. For y equals 4, I've got 1/20th plus 1/20th. There's 2/20ths, or 1/10. And for y equals 5, I've only got 1/20th. So here's my marginal distribution of y. Now, a couple of things to remember is that each of these marginal distributions is itself a probability mass function. So you should always double check that the probabilities in your marginal distributions sum to 1. So here I've got 1, 2 plus 8 is 10, plus 7, and I get 20/20ths, this sums to 1. And I check here again, 4 and 6 is 10, and 6 is 16, and 4 is 20, 20/20ths. This also sums to 1. So it's just a good way to double check your work and make sure that you haven't made a mistake. So next thing we're going to do is we're going to find the probability that x is equal to 0. So since I'm looking for a probability of x alone, I'm going to use the marginal distribution of x and evaluate it at 0. And I can see that this is 3/10 by referring over here to my marginal distribution of x. There's part D. Part E, I want to know the probability that y is equal to 2. Since I'm not saying anything about x in this one, I'm only interested in y. Probability that y is equal to 2. I'm going to use my marginal distribution of y, evaluated at 2, which gives me 2/5. Part F, I'm looking for the probability that x is equal to 0 and y is equal to 2. This is the probability x equals 0 and y equals 2. This is what the joint distribution gives me. Probability of these intersections. So I come over here, 0 and 2 gives me 3/20ths. The next question asks, if x is equal to 0, what is the probability that y is equal to 2? Now this is different because I'm not just saying what's the chance that these two things happen together. I'm saying if I know that x is equal to 0, what is the probability that y is equal to 2? So G is looking for conditional probability. The way I want to find this is by using a conditional distribution. I want h of y given that x is equal to 0. So to find this, I'm going to list for each of my values of y. So y equals 1, 2, 3, 4, and 5. I'm taking f of 0, because I'm fixing x at 0, and y, dividing by fx of 0. So here I have my joint that y is equal to 1 and x is equal to 0 is 0. If I divide that by the probability that x is equal to 0, I'm dividing by 3/10, still get 0. For 2, Say okay. The joint probability is 3/20 divided by the probability that x is equal to 0 is 6/20. So this gives me 1/2. For y equals 3, probability of x equals 0 and y equals 3 is 2 out of 20 divided by probability that x is equal to 0, 6 out of 20. This gives me 1/3. For y equals 4, the probability that x is equal to 0 and y is equal to 4 is 1/20 divided by the probability that x is equal to 0, 6/20 gives me 1/6. And then the probability that x is equal to 0 and y is equal to 5 is 0, so the conditional probability is also 0. And once again, a conditional distribution like this is a probability mass function, and so I need to make sure that the values sum to 1. 1/2 plus 1/3 plus 1/6 does equal 1, so it's a good double check. Now, if I want to find the probability that y is equal to 2, I come here, and it's 1/2. So I've used my conditional distribution. So just to kind of rehash, when we want to find the probability that x takes on a particular value, it's easiest to work with the marginal distribution of x. When we want to find the probability that y takes on a particular value, we work with the marginal distribution of y. When we're finding the probability of some intersection of values of x and y, we use the joint probability mass function. And when we want to find the probability that y takes on a value given that x is equal to a particular value, there we'd use a conditional distribution. The last three parts I'm going to work through are looking at finding expected values. And once again, the easiest thing about finding expected values is to think about which of the distributions you want to be working with to find those expected values. So for instance, if I want to calculate the mean of x, I'm going to use the marginal distribution of x. And what I'm going to do is I'm going to take each value of x in the support, and I'm going to take x times its marginal probability. So here I've got x is -1 times the probability that x is -1 is 1/5 plus x could be equal to 0 times the probability that x is equal to 0 is 3/10 plus I've got x could equal 1 with probability 3/10 and x could equal 2 with probability 1/5. And if I simplify my math, I get that the expected value of x is equal to 1/2. And I've used the marginal distribution of x to find the expected value of x. Now when I want to find the expected value of y, the mean of y, again I could notate this, the mean of x. Here I'm going to find the mean of y. I'm going to use the marginal distribution of y. This is the easiest way to do it. So I'm going to sum over all the y's in the support, y times the marginal probability that y takes on that value, little y. So y could equal 1 with probability 1/10. Y could equal 2 with probability 2/5. Y could equal 3 with probability 7/20. Y could equal 4 with probability 1/10. y could equal 5 with probability 1/20th. And if I simplify, I get 52/20ths, or let's see, 26/10ths. So that would be our mean of y. And again, when I wanted to find the mean of y, I use the marginal distribution of y. And then the last thing I'm going to do is calculate the mean of y given that x is equal to 0. Here I'm going to use the conditional distribution because I'm finding a conditional mean. That distribution I found earlier. Here it is. So I'm going to sum over all the values of y in the support, the conditional probability, of that value. So for 1, conditional probability, given that x is equal to 0, is 0. For the value 2, the conditional probability that y is 2, given that x equals 0, is 1/2, plus 3 times the conditional probability that y equals 3, given x equals 0, is 1/3, plus 4 times the conditional probability that y is equal to 4, given that x equals 0, is 1/6, plus 5 times the conditional probability that y is equal to 5, 0. This is going to give me a mean of 2 2/3. So the key thing here is just to make sure that we're understanding what the marginal distributions are useful for. They're useful for finding probabilities that x takes on a particular value. We could use the marginal distribution of x. If we want to find the expected value of x, again, we can use the marginal distribution of x. Same for finding the variance of x, for instance. If we are working with only interested in y, if we're trying to figure out the probability that y takes on a particular value, we'd want to use the marginal distribution of y. If we want to find the expected value or the variance of y, we'd use the marginal distribution of y. And when we're interested in a probability of an intersection, that's what the joint distribution is for. And finally, if we have a situation where we want to know if x takes on a particular value, what is the probability that y will take on a value? That's when we want to use a conditional distribution. And we would calculate the conditional mean using the conditional distribution. Hopefully this example gave you a chance to sort of work through things, check your work, and then hopefully clear a few things up. If you find that you have any questions, please let me know. Have a good day.